Okay, now we are going to have two back-to-back talks by Professor Zhanpeng from SUNY Buffalo. Both are going to be on sign language, and the first one is actually on how do you build interpreter using wearables.
Yeah, okay. All right, yeah, thanks to Rajesh. And, hello everyone. Unfortunately, my students have some visa issue, and also another student is, waiting for the new baby, so they cannot come to give the talk. So I have to introduce our recent work on behalf of them. And I would like to take the privilege to slightly change the order of the presentation, because the first presentation talk about the virtual IMU things, and which is very relevant to that. And I think I want to present the SignRing first. And sorry, Rajesh. Yeah. All right. So let's start with this. And I think when we start to work on that, I didn't personally realize that how popular the problem for the deaf and the hearing loss. How large population in our community. And actually in U.S. we have nearly we have over 38 million people suffering from the hearing loss, and in the world is almost 1 out of 5. So this is the big problem. But previously, and people start to think about how to bridge the communication gap between the DHH community, the deaf and hard of hearing community, and also the hearing people. And basically, this is a two-directional communication. One direction is how to make those deaf people to understand what we are talking about. This is actually relatively straightforward. Why? Because right now there has been very mature, speech recognition technology, and we can easily, transcribe all, to generate all those captions, and they can read it. But on the other side, there's have been always a challenge, because very little hearing people can understand the sign language, which is the primary communication vehicle for those DHH, community. So how to address that? And we want to mention that in sign language, most of the previous work focused on the manual marker, and which is the manual signs. But there are also another very significant portion of the work, the element of the sign language is non-manual markers. So for example, like the facial, your head movement and all of those. So in this, in this particular study, I think as my, researchers from Georgia Mason, they have just introduced. And the key is there has been long, discussion and argument between the approaches, how we can achieve the sign language recognition. So one is based on the wearable, and the one is based on vision. The vision-based one, obviously, is people argue that is more accurate, and also there has been a huge amount of the data set, publicly available data set online. And but the problem, actually, the vision, vision-based solution is not welcomed by the DHH community, the deaf community. I talked to them very specifically about that. They say that this is kind of like a discrimination and a very offensive, approach, because nobody wants, a facial camera, a camera always face them, and when they talk. And there is also many privacy concerns. The wearable solution, on the other side, is kind of more user-friendly, affordable, but we agree that is less accurate. It's less accurate given all those challenges. For example, the complexity of the sign language and the different gestures, diversity of the devices. So another major bottleneck limitation for the wearable solution is, given the complexity of sign language, whenever you design a new device and you have to recruit a large amount of the human subjects, participants, and try to make them to sign different gestures in order to build a reasonably good model. So, but this is very time-consuming and have spent a lot of efforts. And this is some existing wearable-based solution. Back to the year of 2019, and people try to use the smartwatch and then try to use some self-developed the hand sensor, the finger sensor, or even some ring type device. We need to consider that in order you really want to develop some meaningful device for the deaf community, you need to make sure that this device is really welcome and acceptable for the people then. So you shouldn't use any complicated or cumbersome device. You need to make it easy and affordable. So this is a vision-based solution, and I won't spend too much time here. Now, how we can handle that? Inspired by work from the work done by our colleagues from Georgia Tech, and they work on this IMU tube work back to 2020. And also they have a following paper in 2021. So the key idea is all human activity recognition, using wearables, they have all the same problem is how to collect the data. It's so hard because given the different configuration, different setup of those devices, you all need to collect the data by themselves, by each individual group. And that is really time consuming, and also the data set is very limited. Sometimes it's restricted the capacity and the accuracy of your model. So what we can do is how about we can leverage the huge amount of publicly available videos online, but obviously this is coming from a different modality. And we want to make the transformation. We want to create a mapping function, how to map those information reviewed from those videos, and then we can convert them into the virtual IMU data. And they first to propose the study from the physical activities. And inspired for that, and we try to do something is we propose our own design is based on the ring type design. The reason for that is we considered smartwatch before, but we realized that the real sign language involve very subtle, the finger gestures, and sometimes those finger gestures cannot be well captured by the smartwatch because smartwatch is on the wrist. So we needed the rings, and also the ring could be a very good good device to capture those subtle subtle behaviors for the fingers. So that's the key design. And given their discussion, we just skip the idea. So we want to capture the video, the key motion characteristics based on those videos, and then try to go through those the coordinate extraction and convert them to the 3D coordinates for the sensors on the fingers. So in this case, we will do the signer, and then we extract the IMU, and we obtain the different virtual IMU coordinates from the just like a ring type on the MIP joint. And then we use the VGD model, and this is our prototype design, the hardware prototype design. We have, this is a proof of concept, and we just use a 2 IMU sensor on the finger. And we can see that from this figure, we can see that the similarity between the real IMU collected and the extracted virtual IMU collected, how similar they are. So this is the key, goal, what we want to achieve. And based on our evaluation, and unsurprisingly, we can see that ultimately the goal is, okay, if we can extract all the virtual IMU from the public videos, and we can use that solely for the training of the new model. But we know that this is from the data set, we need a little bit of calibration. And we can see that when we use all of those virtual IMU data, and we can achieve the relatively higher the error rate. But when we add a little bit more data from the user, user do some calibration data, and the error rate will be reduced significantly. And we also do the ablation study and remove one direction, and also we can do the remove the one non-dominant hand using only one hand. This is the evaluation for the training percentage. Okay, we see that when you use all the data, the training data from the virtual IMU, we have a higher error rate. But when we add some user personal data, and the error rate will be dropped significantly, and also the vocabulary size. And we can generate a vocabulary size up to almost 1,000. This is, one of the first study really has this size of the vocabulary in the sign language analysis, recognition analysis. All right, so what do we want to discuss? The main takeaway of the study is the training overhead represents the total time for the data collection. We can see that in the previous studies, the training overhead is almost like 20, 30 hours, because including the time you collect all the data and you put those data in the training. But theoretically in our work, and offline analysis of, besides the offline analysis of those video data, the real training effort is minimum. So we can use those online videos to generate a huge amount of the virtual IMU data set, and then to create a very good model for that. So this is one-time effort, and we see that this can save a lot of time for our work. All right, so that's it. And any question?
Yeah, sure. Thank you for the great talk. And this is a interesting coincidence because I'm from Georgia Tech, and also I work on IMU as well, where we're trying to convert videos and text into virtual IMU data. So earlier this year, we actually had the exact same project where we're trying to use IMU to convert videos, ASL videos into virtual IMU data, actually using rings as well. So, and once we saw your paper, it was like, this project's screwed. Yeah, but again, very interesting talk. And a question I had was that, is there a reason why you're using like hardware you're developing instead of using commercial hardware like such as tap strap, like a wearable keyboard, also with rings that also have IMU? Is there like any advantages that your hardware brings?
Okay, yeah, that's a very interesting question. So the reason for that is we want to choose our own IMU because there are, although we see that there may be some commercial devices like we see the smart rings right now, they have the IMU, but we think we want to have better control. So where we put that ring, because we don't want to spend time to configure the position where the ring is going to be located. So we need to try a few times and say, okay, let's just use our own IMU sensor to see, okay, what is the best position and how to configure that. And we don't want to be restricted by the existing, commercial smart ring design.
Got it. Thank you.
Mm-hmm. All right.
Sorry, it's a talk on sign language. I have to use the mic. Given the variety internationally of sign language, and for instance, British sign language, you hand spell on both sides. Do you have any thoughts of how your tool would work for, say, either of the Chinese sign languages or one of the many Mexican sign languages? Thank you.
Thanks for the question. I think that whole approach, fundamentally is transformable to all different languages, because what we need is just we find their corresponding, the video sign language data set. That's it. And also there are huge, huge data set, resourceful data set is although right now given the environment for the more inclusive environment, and all of those news report, video report, they have the signs. So this is perfectly labeled data. And we want to take advantage of that and to see what we can do, to create an even largest forever, the data set for the sign language.
Now I'm going to introduce Zhanpeng again. And this time he might actually talk about what I actually introduced him previously, which is using building wearables to do sign language.
Okay, yeah. All right, thanks, Rajesh. Okay, so if you can recall that in the beginning of the previous presentation, I talked about in the sign language recognition, there are two important elements. One is menu marker, the other one is non-menu marker. Unfortunately, most of the existing sign language recognition system, they primarily focus on the menu markers. And most of them neglect the non-menu markers, although this can be done in the computer vision, using the computer vision approach. But given the limitation and the issues I just talked about, in all existing wearable-based solution, they don't consider the non-menu marker. But this lose a very significant portion of the meaningful ways to convey the communication in those hearing people, in the deaf people and the hearing people. Okay. So we know that for the menu marker, it's just all those gestures and signs, and they have they contain the hand shapes, hand trajectory, orientations, and a non-menu marker, including the facial expressions, hand tilting, shoulder raising, mouthing, and all of those. They are very, very important. The problem is, it's actually so hard to be honest, it's it's actually very hard to recognize the non-menu marker using wearables. Think about how we can do that. So here, a little bit of background for the ASL is we actually needed the ASL glosses to the nature English. So this is the way how the glosses stand for the signs using the nearest translation of the signs in English. So those are the basic element, in the sign language. And what we really want to do is see how we can build a real end-to-end solution in the communication. So this is all the background. So the computer vision one and the wearable-based one and the wireless signal-based one, they all have their own pros and cons. But what we want is in the daily communication, what we can do. So we definitely want to even you have some way, you have the wearable device, and you can recognize the signs, but how do you really allow the hearing people as audience to understand the part? So this is a smooth communication. That's what we are looking for. So obviously you need to have a way at least you can concurrently recognize both the manual and the non-manual marker. You need to be user-friendly and privacy-preserving. And also we can have the translation, not only the recognition. The translation is different from the recognition. We need to achieve the translation in real time. So the challenge one, how to distinguish the subtle non-manual and the manual markers simultaneously. So we try to find a solution, from the previous great, research work in the literature. And there are some studies before they used either IMU sensor in smartwatch for the hand gesture recognition, like the sign speaker in UbiComp, and also someone tried to use the IMU sensor in the earbuds for the facial gesture recognition. So what we see is we want to combine the different sensing modality for non-manual and manual markers recognition at the same time. So using the earbuds, the IMU inside the earbuds, we can potentially detect your facial expressions and also their head motions. Head motion, and when you have the head motion, we have the shoulder movement, and all of those could be captured by the earbuds. And also we have the smartwatch to recognize the gesture, the hand gesture. And this is the approach flow, and we can see from the regular signal processing, and we go through the continuous wavelet transformation, and we have the inversed CWT. We try to identify those symbols. Here we have mixed signs and also the non-manual markers, the head movement. So this part will be detected. And we used, because we are going to collect the two different channels, the IMU data from left and right the ear. So we built the separate independent CNN model for that, for the recognition task. And for the manual marker, and we used the Doppler effect and the spectrogram extraction, and we built the CRN, the convolutional recurrent neural network model for the high performance. The challenge two is how to translate the ASL glosses into the natural English. This is another challenge. So we shouldn't just stop there to say, okay, recognize the corresponding glossars, because the sign language, they have their own unique linguistic. It's not something you get all those words and you link them together, that will be a natural English. So existing work try to use the encoder-decoder structure for this translation, but normally it needs a large number of samples. And this problem can be treated as a language translation problem, so we want to get the answer from the text-to-text NLP problem. We will fine-tune a well-trained translation model, the T5 model, the T5 transformer for our translation. And this is this whole system framework, and we can see that we try to get both the non-manual marker recognition as well as the manual marker recognition together, and then we go through the text translation, the T5 transformer model, to generate the corresponding text. And now we will synthesize the text and into the real speech and go through this small speaker, the wearable speaker. And that means whatever the signer is performing is signing, and the corresponding communication language, what we call, is going to virtually speak out through this wearable speaker. So this is the way we really want to build the end-to-end solution to facilitate the communication between the signer and the hearing people. That's the whole system work. And we select the sign language words and sentences. We recruit 10 volunteers, including 3 deaf people and other ASL learners. And this is our system design, including the earbuds, the smartwatch, as well as the wearable speaker, and the whole hardware system together. And we can see that the performance, the accuracy, obviously for the native sign language speaker is much higher. And than the learner, than the ASL learner, just because for the learner, they're not fluent in this, and somehow they have more significant variations in their signs. But this is still, very good accuracy level. And also we consider, in order to show that if we do not consider and ignore the non-manual marker, what is going to happen? We can see that without the non-manual marker, the error rate is much higher when compared to the case when we consider include a non-manual marker. So typically, according to the statistics analysis, normally the non-manual marker is going to take like 20 to 30%, 20 to 30% the grammatical meanings in the sign language. And also we perform the leave one user out and the study evaluation to see how it works. So we can see that this is 2 subjects and their earphone data and the smartwatch data. And the calibration sample, just we want to evaluate to see, okay, how well it performed when we have more calibration samples. And when we have more data from the user, it's him or herself. And unsurprisingly, when we have more calibration data and the accuracy, the error rate will drop significantly. But initially, that means, okay, as long as you give a little bit of personal data collection, we can generate a very reasonable system. So the conclusion, and obviously I saved some time because skip the background. So we proposed the smart ASL, sign language gesture recognition system that leverage user-friendly earbuds and smartwatch to recognize the ASL. Compared with existing wearable solutions, smart ASL is a novel system recognize both the manual and the non-manual markers at the same time and translate ASL glosses into natural English. And we design our proof concept prototype and demonstrate the feasibility of this idea. And the last thing I would like to mention that I think, according to the past few years, we working these, those projects and our close collaboration with the deaf community. What I learned is sometimes there is a huge gap between the idea of the researchers and the demands, the real demands of the deaf community. Sometimes we think this could be a good idea, but actually that may not be, well acknowledged and welcomed by the deaf community. What they really want, you need to think about from their perspective is what they want. So sometimes when I talk to them, they say, okay, so if you have any, I know many years ago, researchers always want to work on those wearable gloves because the gloves may be very accurate. But the deaf community stay strongly against that idea. Say, okay, why should we add those extra efforts and to get those devices in order to allow you to understand what I'm doing? So this is the very big, very important, insights. What I've learned is you need to think about from their perspective is we want to provide the most user-friendly and affordable solution, not only for the accuracy-driven, it's for the usability-driven, the user-driven. So somehow we skip many great, accurate, or more precise solutions just to stay with the current one is because we see this is something that may be helpful to bridge the gap and to really help those community with the demands, not just think about it from the research perspective, say, this is great, this is very accurate, but they don't need it. All right, thank you.
Thank you. Any quick questions for the...
Yeah, thank you for bringing this up, and thank you for the great talk. And especially it's the idea of the glove is not what the deaf community needs, and this is also what we've been talking about in our group as well. So coming back to the social acceptance, so in this work we talked about earbuds and rings. So what do you think about the social acceptance of the smart rings and the earbuds? Do you think the deaf community is going to accept them, or is it going to have a lashback similar to the gloves?
They are okay with the rings and like the earbuds. Someone may argue, okay, why they needed the earbuds? Because right now there is a trend. I can tell there is a trend for the conventional hearing aid industry. So they will combine with the latest the earbuds design, and this will become very popular and common assistive device for those hearing people. It's not the conventional idea. Okay, the hearing aid is a different device. So right now this is the converging of the hearing aids and the earbuds together. So they need that in their daily life, and they, as long as what I heard from our collaborator, and they think this is great.